All right. So I'm hoping that this rings some bells with what we covered in Unit 1. We'll see. Or not Unit 1, the previous unit, Unit 3. I'm just going to jump right in there. We don't have a strong acid anymore. We actually have a weak acid. And actually coming up, I can't decide what I want to do. I might just go ahead and kind of diagram it up here. If you're faced with this problem, right away you should take the weak acid and write the equilibrium. Okay, so we'll go ahead and do that. Of course, if it's a weak acid, it's going to kick off a proton. I bet it's this first one, HC6H4NO2 in equilibrium, kind of like we talked about Friday. Kick off that proton, H plus. Plus what's ever left. Wow, that's even worse. This one's really dark, but it's blobby. C6H4NO2, and hopefully we're all good with that. I'm going to give it a negative. Okay, it's ionizing. This is a weak acid. We can write the Ka expression just kind of like we wrote the Kc expression. It's the molar concentration of H plus times the molar concentration of this thing. We're going to call it the conjugate base on Wednesday. C6H4NO2 negative divided by the molar concentration of, this is what we call the unionized weak acid. Stuck together, unionized. Molar concentration of C6H4NO2. All right. What else we got? Okay, so it says that we have a solution that is, when they prepared it, I'll just put prep. When they prepared it 0.012 molar of that weak acid, HC6H4NO2. Okay, they prepped it like that. Now, to a certain extent, that ionized according to this equilibrium. Then they went ahead from their solution. They said, well, this solution has a pH of 3.39. Smiles all around. Acidic? Well, I hope so. Okay. But do you see where from the pH, part of the important part of this problem is from the pH, we can, and you're doing it in your homework for part 2, we can knock out the hydrogen ion concentration at equilibrium. Make sense? All right. So I'm going to finish that thought and then I'll kind of march through the slides for this problem. This actually is an initial change and at equilibrium sort of deal. Our columns correspond to these 3 things. So I'm going to make a column for HC6H4NO2, molar concentration. I'm going to make a column for H+. I'm going to make a column for C6H4NO2, negative. Now, the way you read this is the initial concentration. That's like as you prepped it. Do you guys buy this? That as you prepped it, you had 0.012 moles per liter of your weak acid. As you prepped it, we are basically, and I think I have a slide to show that I understand autoionization means that this is 0, not 0. It's actually at least 1 times 10 to the minus 14th, excuse me, 1 times 10 to the minus 7th at 25 degrees Celsius. But we're going to go with 0 because it works fine. It's not enough to screw up our answers. So initially, this is what we have, okay? I don't know the change yet, but I will. We can, our thing is going to be to plug that, use the pH to get the molar concentration of the hydrogen ion. Okay? Then we know from stoichiometry, actually, it's kind of, we've got the boring 1 to 1 to 1 here. Once we have this change, which we can get from the pH, then we can get this change and this change. Take our initial, apply the change. We can knock out these equilibrium concentrations and then plug them back up into there. There you go. It's one big thing just like we worked at before. In italics, note that this corresponds to the type of equilibrium problem we covered in Unit 3 in here, where you know one equilibrium concentration, as given by the pH, we're knocking out Ka, which is like knocking out Kc. That's it. That's it, that's it, that's it. Okay, so yeah, I kind of got ahead of myself. In working this problem, you really can't work it correctly unless you go ahead and write the equilibrium for the weak acid. You got to recognize what it's doing, kicking off a proton. Okay, we can write the Ka expression from that. Do you need to? I think so. Because honestly, here in a minute, we're going to plug into this Ka expression. What are we going to plug in? We're going to plug in these equilibrium concentrations. Just to emphasize this, remember when we had the Kcs and I kind of said, well, you could put a little subscript E here? Those are equilibrium concentrations. That's this last row on an ice table. The black doesn't fit the blue. All right. So like I said, and you know, this takes the only way most, you can flourish in chemistry if you have an aptitude, but you have to work the problems. So in order to know what you're doing, you need to work these problems. Initial molar concentration of the hydrogen ion, like I said, we're going with 0, but we know it's not 0. I have a slide to kind of describe what that means. pH, we can knock out from, the hydrogen ion concentration we can knock out from the pH. We take 10 raised to the negative 3.39. And when you do that, we'll come up with 4.1 times 10 to the minus 4th. And things start to fall into place. 4.1 times 10 to the minus 4th. Blobby pen, blobby marker. So that means that this was this change. And the stoichiometry is a 1 to 1 to 1. So actually, this was what was formed. Okay. This is also going to be what was formed of the other thing, which is the conjugate base. 4.1 times 10 to the minus 4th. Of course, over here, we're going to put minus 4.1 times 10 to the minus 4th. It's exactly what we did before. All of that from a pH. So here's my slide to say, is this a valid assumption? If we were to assume it has the quantity that you get with autoionization, ballpark of 1 times 10 to the minus 7th, actually that's not going to change our answer because of magnitude. That's 3 magnitudes smaller than our change. Okay. The other thing is, because of the common ion effect being our weak acid is going to provide some protons, some hydrogen ions. Actually, that is going to diminish the amount of autoionization that occurs because of the common ion effect. Okay, so if you're good with that, I'm good with that. So at equilibrium, okay, we can take the initial and apply the change. Oops, this is one, yeah, this one's over here. So at equilibrium, this is 4.1 times 10 to the minus 4th moles per liter. Okay. The other one, we get to do this subtraction, okay? Remember, if we're subtracting, we round according to decimals, okay? And so honestly, in this case, we're going to see that this change is not even a blip to make an effect. If you put this into your calculator, take 0.012 minus 4.1 times 10 to the minus 4th and round according to 3 decimals, you're going to get 0.012 back, is my point. If you apply the rules of rounding like we know we need to do. So that's pretty cool. Okay, so 0.012 moles per liter. Now, all we got to do is plug them in and get our Ka. That's it. That's it. So in the top, for the hydrogen ion, we put 4.1 times 10 to the minus fourth for what I've been calling the conjugate base, that C6H4NO2 negative. We also put 4.1 times 10 to the minus fourth. For the molar concentration at equilibrium of the weak acid, we decided it's basically the same, 0.012. Round to two significant figures, and you get 1.4 times 10 to the minus fifth. So that's the Ka value for that weak acid, okay, given this information, how it was prepped, and the pH. Yay. So these will also be due on Wednesday. And these look like this. Now, the problem with these problems is it goes back to kind of Chem 1 a little bit. So you're going to have to get the molarity of the weak acid. That's that CH3CH2CO2H, okay, propionic acid. You get the molarity from the moles and the volume. But other than that, it's kind of like we've done here. In this case, you weren't given a pH, but by golly, you were given the equilibrium concentration of the hydronium cation, which is the same thing as the hydrogen ion. Okay, so I would work it with an ice table. If you don't work it with an ice table, you need to show your quantities, show all additions and subtractions, and how you got your equilibrium concentrations. So it's just very similar. Okay, yep. Very good. And then the next one is another weak acid. In this case, you get to go from grams of acid per liter to moles of acid per liter, the weak acid. Do that front end work, and then prepare an ice table and plug in to get the Ka. All right. Very good. 30 seconds to go.